So, good morning, everybody. Thank you so much for your patience here in the theater and also on the live stream. We had some technical difficulties, which you know can happen. And I want to say a big thank you to Vladimir, who has bumped up his speaker slot to go first so we can try to solve the issues that we're having. So thank you so much, Vladimir. And I won't waste any more time. Please, show us what you're going to show us today.
Hi everyone, my name is Vladimir. I have been using D since 2006. I've also contributed to things down here and there. I'm super excited to be here, and today I want to try answering one part of the question which I always get asked. Why D? Why do I like deprogramming so much? Why do I write everything that I can write in D? And of course, one of the biggest aspects is metaprogramming. And well, the talk that was supposed to be here was called Things That Matter. Unfortunately, my talk will not be about things that matter so much. I'll be talking about a few personal projects in which I have used these metaprogramming to great success. So I'm going to start with serialization because it's one of the things that D does really great. Let's start with a simple JSON example. So I guess everyone here knows JSON. If you need a reminder, it looks like that. And a very simple problem that comes up often is like you have a struct like that and you want to convert between them. And as far as I know, this is one task which is literally impossible to do in C++, even in the very latest versions. Like without having some kind of metadata ahead of time, you just have a type declaration and convert the two. But it's absolutely trivial in D. And I would like to show you quickly how it's done. Well, one way to do it. So if you want to serialize an arbitrary type, you will probably want to take a arbitrary type as a template function, as a template parameter, and do a static if. You could also use contracts. But you can use static if to check whether the type corresponds to a certain subtype. This is using is expressions. You can also use std.traits or __ traits for some other things. I cheat here a little bit because I use these format functions to serialize JSON literals. And although they do some things in common like escapes, this is just a shortcut for illustration. If you want this, so this function serializes to JSON if you want to go, and the structs are a special case here because you also want to descend inside the struct and serialize all the members. So here what you will probably want to do is use a for each with tuple of. And tuple of does a huge part of the work when it comes to introspection. What it does is it expands to a tuple of all of the struct's members. And this is not the only way to do it. You can also use __ traits get members. However, note that that will also get you the methods. So what this does is it iterates over the expanded tuple of all the members in the struct V, and it gets the name of each identifier in the struct. So note that here we use v.tuple_of, and then we use the index variable. The reason for that and why we can't just use trace get the identifier of the field is because then you just get the string field, which is probably not going to be very useful. So this is a basic example. Just append a comma and wrap it in the curly braces and move on. If you want to do it the other way, it's also very similar, and you can just look at the type and parse it depending on the type and return the type. We have to explicitly specify the type we want to return here, obviously, because we we want to specify which type to deserialize in. And, well, this is a simplified example. It doesn't show checking if S is at the end, so for trailing data. You might find this useful if you're trying to parse JSON embedded in another string. As for structs, well, it's the same thing. You want to iterate over all the fields in the structure and check if the name corresponds with the JSON field you've just read. And, well, there is a slightly better way to do this because this expands to a bunch of if expressions for each slide, and instead you can do a for each inside a switch. This will generate switch cases for each member of the struct. But take note, if you use this method, make sure to use a label when you break out, when you end the case statement, because otherwise you will just break out of the for each statement. So it's important to use a label there. And this is a practical example. This is a fragment from the web interface from Digger. One of the convenient uses for JSON serialization that I found in D and I use all the time is when writing backends for web applications, because this allows very easily to just define a format for your data as a D type. Then you fill it out and you make a wrapper function which just serializes into JSON and sends it out to JavaScript. JavaScript then reads it back in and parses it and does the web frontend, whatever you want it to do. So this was a quick introduction to serialization. And well, a few years ago, I had this JSON code in my personal library, and for a project, I decided that I needed a real serialization library. Well, I started working on one, and fast forward a few weeks, and I had 5 DMD pull requests open, and I was up to my neck in trying to fix a backend code generation bug, and I was still not very close to a serialization library. But I did discover some interesting tricks along the way, some interesting things which I'd like to share. So alias binding is an element of the deprogramming language which I'm very interested in. So you probably know alias template parameters. An alias parameter can take anything, a type, a template instantiation, a literal, a function, essentially anything. It can also take an overload set. It distinguishes between the two. So here is a simple example. We pass n as an alias, and then prints it, obviously. But it can also take local variables. Note that even though printed is declared outside of main, it is still able to print the value of n, which is a local variable inside main. So what happens here is that when we pass a variable that is inside some context, so it is a local variable, or a struct field or a class field, and it has some context attached to it, so we can't reach it through global scope. It is passed along with the alias. So what happens is the function, well, I think this is the technical term, the function becomes nested within the context. So it is as if printed was declared inside the main function. This has a lot of interesting uses. However, has some limitations. So who knows if this will compile? Yes or no? 10 seconds.
No.
No, why?
Cannot pass local symbol to non-global template.
Could you please speak up?
Something like cannot pass local symbol to non-global template.
Yes, because print is already a non-static method, so it needs access to the I variable. But it also receives the B variable as an alias parameter. And currently, we cannot have, well, a single function cannot have more than 2 contexts. Understand that this is a limitation which is not a language limitation, it's a implementation limitation. I think some experimental compilers, Amori, where are you? How is SDC doing?
SDC is gonna compile that, it's gonna just create 2 contexts and run with it.
Okay. So currently this does not compile because print already has a context. And you can see this more clearly in Phobos if you try to use task pool from STD parallelism and try to use any of methods on it. So it has methods like map and amap, I think reduce, which take a lambda as an alias parameter. But because these are methods and not global functions like those in std.algorithm, this doesn't work as well. Because if you try to pass a lambda, which actually needs a context like here, increment is a local variable, and if you try to use it inside the lambda, it creates a lambda with a context, and if you try to pass the lambda with the context to a method, that's not going to work. The compiler will say that it cannot pass a, I think it's a delegate literal to, well, it's a this one is a template because we don't specify the type, to taskpool.map, which already has a context. It is not static. Question, what does static mean here? Who knows? It could mean two things. Okay, nobody knows, fine. Static could refer to two things here because you would think that because static is inside a struct, you would say that whatever is inside the template does not use the this pointer, which points to the struct. But on templates, it has a special meaning. Well, actually, it's not specific to templates, but in presence of alias parameters has a special meaning in that because alias parameters allow nesting something inside another one's scope, in the same way that static affects this pointer, static also affects the alias context. So if you sometimes it is useful to pass an alias without the context. For example, this function here refers to the alias A without actually accessing the value. It prints its identifier, it prints its type, and it prints the name of its parent, but it never uses the type. In this case, we do not want to pass it with a context pointer. So there is a way to do this, and this is to specify static on the template, which this means that we will not pass a context pointer when we call the template. So who here remembers my last year's talk? Can someone tell me if this compiles? Yes or no? We use an alias parameter here, and we call it with a field and a method. Who knows?
I think yes.
This compiles. This does not. Because only fields and variables pass a context pointer. So this is one inconsistency I noticed when I was writing my serialization library, and this stood out. This was not always the case. It changed in 2.065, if I'm not mistaken. Right. So the first one compiles, the second doesn't. Oh, before 2.061, methods used to have context pointers, and they were changed. And the second thing is that this will not compile regardless of whether we have static here or not, because we pass the I variable, which is a field in another struct, to the template. However, if we want to actually print it, we cannot access it because the static whether we specify it or not, we cannot specify, because the static here ties off the connection to the template context. So Kenji proposed, Kenji Hara, the compiler contributor, proposed the following syntax to clean it up. And it's something I wish could be implemented, though static alias would mean that we do not want to pass an alias as context to this alias. Another thing which I encountered when writing my serialization library is that even though we have things like passing a field without a context pointer, so we say capital S.B, that's the type, and when we get another instance in print field, and there's no way to attach the instance back to the context/alias parameter. So there is the traits, the get member traits, however, that takes a string. And the way you'd usually do this is you'd use a string literal. However, if you use a string literal, there's no way to distinguish between overloads in an overload set. Another way Stenial suggests is to use a lambda instead of an alias. However, then you have to make sure if you want to write to it, you have to make sure it returns ref, and you can't use traits identifier on the lambda to get the name. And I implemented this in a experimental pull request, and something that helped me write the serialization library, which I would like to discuss quickly. And this syntax came up, but well, it doesn't matter. So this is part 3. There is a problem that comes up with when you try to write small composable components. And std.experimental allocator, which is pretty awesome, currently does composition by adding a field. So it does, this is the usual pattern used in allocators. If you use state size, if it checks if the parent allocator has any size, and it adds a field. Otherwise, it just creates an alias. Well, that's all fine until you want something like to have multiple components refer to the same base component, or the diamond problem. And there is no obvious way to do this. And C++, you will probably use multiple inheritance with all its flaws and quirks. In D, we do not have that. So the way I use this in my serialization library is that I found a way to do this, which is each component has a data and implementation part. So the data is a regular struct which declares the state of the component, and the implementation part takes an alias to its data field. And this actually allows us to compose multiple components together in a way that allows them to refer to each other without having to use something like pointers, or of course multiple inheritance. So as an example, I will show you something that calculates a simple example which does like an expression tree. We have 3 variables, and we want to add x and y, and then y and z. So we refer to y in both of these adders, which will be separate components. Then we want to add the result together. So just to warn you, you won't be able to run this with a regular compiler right now. I have published some patches on GitHub. However, you can, right. You will need to specify the static either on the template or on the implementation template, so that we make sure that we do not we receive context as actually, well, whatever. I'm sorry, I thought I had the second slide to rehearse this. So this is the implementation of a simple adder type. It takes two alias parameters which specify which are to be added, and we have a dummy argument here. All this dummy argument does is that the template inherits the context passed to the A variable. And we add a simple method here to add the two. This component does not have any state, so it only has an impl part. And this is the formula that we have. So this is the variable. We will just store the integer value. And this is first we declare the data part for the variables which are to be added, and we add the implementation parts, and then we add the adders together. So note that for the implementation, we pass as an alias parameter the data parts. And this allows us to refer, in the adder, to refer to x, y, and y, z. So we refer to the implementation part, which then refers to the data part. So once you declare that, you can specify the values, and it allows you to get the final value. I have used this in my own allocator library, which predates std.allocator. And the nice thing about this approach is that everything shares the same this pointer. When you use typical composition, you usually have each object has its own this pointer. So if it's not optimized out, there's going to be some calculation in passing. But this allows inlining to be much more aggressive. Even though it's verbose, it can sometimes provide a performance advantage. So I won't talk about my serialization library here. I just mentioned that most serialization libraries, which I've seen, the common thing between all formats that they support is a certain state, whether it's a dump tree or a serialized native type. What an interesting approach I found is that instead of using a common state, is to use a common protocol. And this allows you to write protocols which then serialize to or from to certain states. So if you have a typical serialization library would serialize to and from a DOM, you can implement that as a protocol. Same with serializing to types. And of course, since the common state is a protocol, you can also add transformers, which are like filters in the protocol, allows you to do transformations on hierarchical hierarchical data structures. And you can serialize directly between any formats because, of course, it's without any allocations because it's part of the protocol. You do not need an intermediate state between serialize between two formats. And if you want to look at it, the code is here. And this concludes the third section. OK, who here likes video games? Great. So I like video games too. And if I particularly like a video game, I will sometimes begin to tinker with it, take it apart and see how it works, maybe make some modifications. And this is my one of my first deep projects concerning game modding. Who here remembers Newgrounds? The website, great. Newgrounds used to be, well, it still is a website where they had tons of Flash content, including games. It was one of the things that made Flash games very popular, and well, there were lots of Flash games made on that era. It was one of the bigger platforms for independent game studios. A lot of Flash games that started out on Newgrounds now are commercial titles or game series that you can buy on Steam. And RabbitCD awesome it stands for Vladimir is bad at naming things. Laugh track, please. And it targets specifically the ActionScript bytecode of ActionScript version 3, which was released in 2006 together with Flash Player 9. Before that, it used a different, Flash used a different, slightly different language. In version 3 is optionally statically typed and uses a completely different execution model. It runs in a virtual machine, it compiles to bytecode, and I believe the Adobe's implementation JITs it. So there were no good tools at the time for working with compiled ActionScript code. So I had to write my own. And one of the problems I had with writing RabbitCD is, well, the ActionScript bytecode format has a lot of different types, and a lot of them are discriminated unions. And I needed to do a lot of things like, serialize them, and I needed to compare them because I need to use context pools, I needed to stringify them. This is another discriminated union example. We have lots of discriminated unions, as you can see. We have some with extra fields, so I couldn't just use a cd variant, which did not exist at the time because this was in 2010 before even D2 started out. Well, it was just starting out. So each type had to implement these functions, and well, currently the decompiler does a pretty good job of implementing them in many cases, but of course, if you have unions or even discriminated unions, it's not going to work very well. And because I had a lot of long list of types, I did not want to implement them by hand. It would probably be a bad idea because if you had to change something, then if you got to change something else, you would get strange bugs. So the way I went around this is to implement mixin, which you implement a processed data function which takes, well, this uses string mixins, and you specify the logic of how to traverse your type. Using, it receives a handler type as a template parameter, and you specify, so if you have a discriminated union, you do a switch. If you have multiple or optional fields, you do an if. And this will, well, if you mix in auto-compare and auto-to-string, this will do the right thing and generate all those methods to string, op equals, opcmp to hash. You need opcmp for sorting, you need to hash, and op equals for associative arrays. And I will not show you the implementation because it's old code, which is written in D1 code. And as for the rest of the file format, the Flash file format, well, it is even worse than the ActionScript bytecode format. It is many, many pages long and has lots of data types and has lots of inconsistencies. It has things like we specify the size of the following fields as the first field, which is also the number 5 specifies the number of fields. So then we have to take n bits and read n bits 4 times, and that gets us a struct. And normally you would do something like this. But if you, well, there are lots of types, and doing this by hand is error prone. And if you want to do other things like serializing it back to the Flash file format or traversing, you will not have a good time. There will be lots of boilerplate code. So the solution I came up with is to define something like a DSL. D allows us to define DSL. Well, you can use a simple string and parse the string as a single file. You can even put it in a separate file and read that back in and parse it. The way I did this is to use some D types, so it is not completely a separate language because it uses D syntax. And if you look at this is how it looks in the manual, in the specification of the Flash file format. And this is how it looks in the code. So mostly I would just copy and paste it, and it just add some syntax, and it would generally work. There are more complicated types as well. For example, we have optional fields. This is also one of the simpler types. There are types definitions with pages long, and it would be not very practical to implement them by hand. And this is how it looks in the ABC DASM right now. And we have a third field here which specifies the condition. So not all types can be fit in this. Well, like I said, the specification is not very consistent. So sometimes you need to add custom logic, in which case you can just add a custom implementation. So I invented some syntax here. Writing your own DSL, of course, allows you to come up with any syntax you want. You'll generate code which parses it out and generates the right code. Here I write some custom methods to read the last 2 fields because well, the way character is bound is that the first field of the next character is 0, even though it's sort of part of the next struct. It indicates the end of the record. So the code is pretty boring. I will not be showing here, but it's pretty simple. The basic idea is to just use string concatenation. It starts out like this. You will iterate over all the fields. Because we pass the specification as an array, we do not need to use tuple of here. Just iterate and generate the code. It's very basic string processing, and it's really great that D makes it so simple. You do not need to use a separate build system. You don't need to put it in a separate file. You sometimes get good error messages. And one weird trick, well, I ran into a problem with my project because sometimes compilations started to take, as I added more types, it started to take minutes and then hours. And until I realized what was happening, and I found this one weird trick that made my compilation times go 100 times faster. It is to add this at the front of the function. What was happening is that my struct was also being compiled to machine code, even though it was also only ever called during compile time function execution. So if you add this at the front, it's going to short circuit it and avoid any optimizer problems with, even if well, taking 1 hour is probably a bug, but even if the bug was not there, this will likely speed up compilation of CTFE heavy problems. Of course, well, yes, the problem is not with the CTFE, just to make it clear. It's with that we are compiling code that should only be executed as CTFE. And well, I'm proud to say that ABC doesn't start out as a silly little project to play with Flash games, but it's made into a Linux distribution which concerns with, well, RAMNux stands for Linux Toolkit for Reverse Engineering and Analyzing Malware, and it has been included in RAMNux, and I have been glad to say that I've been very interested to find out that F-Secure has been using ABC DASM for a Flash and malware analysis platform. So I think that's pretty cool for a project that started out as a silly toy. Thank you. So as I said, some of my projects aren't very practical. It's just solve everyday problems which I run. Who here knows, well, probably most here have heard of this game. And when this game came out, I proceeded to throw away 1 month of my life on it. But, well, I started playing with it, and I found some things that were missing and I did not like. And I started to look under the hood. And I noticed that the entire game interface, the menus, the HUD, it was written in Flash. So you can imagine my reaction. And I made a small mod, which all it does, for those who haven't played, this game is like a wasteland post-apocalyptic simulator, and most of what you do is walk around, collect junk. Well, there's also some other stuff, but this is the main part of the game. And one of the things that I was missing was a way to show me which junk was worth taking. So what I added was a simple value per weight calculator. So I released that, and curiously, it got a lot of downloads, 114,000, which I think is pretty crazy. And that was pretty interesting. And something else that I wanted to talk about is, well, another use case for D-meta. So that was not really related to D-metaprogramming. But another problem I had with Fallout 4 was that I wanted to run it at a lower resolution because my graphics card couldn't handle it, and it would not run. If I tried to shrink the window, I would get this. And I tried to find a solution to this problem. So I wanted to, the game was calling a function in DirectX 3D API, which was trying to set the resolution, but it did not set the parameters right. So if I knew that function, I would know how to, I could hook it and find what it was, but I could not know what function was. I could spend a lot of time reverse engineering the game, but I figured that there's a simpler way to do this, and which is, I tried to set up a module which would intercept all Direct3D hooks, function calls. So Direct3D is using COM, which is basically a well-defined interface with, it uses interfaces with reference counting. And what we do here is, well, I could have used IDLs and generate interface description languages. We specify the interface for all COM calls in a language agnostic manner, but I figured since I was using D, I would use it the D way. And the way I did this was I enumerated all the interfaces declared in these DirectX headers and generate lookup tables for the interfaces. So what we do here is we look at each module here. Gencode enumerates all the members inside the module, and it looks for all interface declarations. And we register, each interface has a GUID, which is a hex string which uniquely identifies an interface. We register all of those so that we can declare a function for each, which takes the interface pointer and it hooks it to, it hooks all the methods in the interface. Here we enumerate all the methods in the class, and we notice that we also have to do this for parent interfaces because COM also uses inheritance. And this is the function which is hooking a method. This is pretty, there's not much interesting going on here. The important thing is that we have to remove the protection from the memory area because we are overwriting the interface's virtual function call table, which is usually located in read-only memory. We replace that with a custom function, and notice that because this method is templated by the method name and the interface, a new instance will be generated for each method and in each interface. This allows us to declare a variable which is one per each hooked method. This allows us to uniquely store the original function pointer, which we will need to call the original function later, without using additional lookup tables. And this is the function which actually performs the hook. There is not much interesting here. We do some logging, obviously, because we want to find out which is the function which sets the wrong display parameters. But the important thing here is query interface. If query interface is called, we need to find the interface in our lookup table, which is generated by scanning all the modules, and that will appropriately create the hooks for that interface. For each function call, we need to call hook arg, which also iterates over all methods, because many functions will return a new interface as an output parameter. So we do that here, and we also hook its interface. And the rest of the system is complete. All that's needed is to create a single forwarder function. So since the DLL, well, the way the DirectX works is usually in a DLL, there are very small number of functions, and you call those, and you get an interface. And you query those or call methods on them, and you get more interfaces and such, and this gives you access to the entire API. So we put that in a DLL and create the entry point, and the entry point will thus recursively hook the entirety of the Direct3D API. And sure enough, it generates a huge log file. This allows us to find that the function we were looking for is rs set viewports over there, and hooking that allows us to find the function we need to hook. This allows us to to finally release something that other people can use, and apparently more other people found it useful other than me. And to add to Simon's list of things that use better C, well, don't let anyone tell you that you can't make tiny Windows executables in D, because you can, and this is proof because the entire DLL weighs 5.51 kilobytes. All code can be found on GitHub. On to the next part, I want to talk about a graphics library, which I started working on a few years ago. So I mentioned this in a blog post a few years. I want to mention it here as well. So I started working on my own graphics library because I needed a programmatic way to create and manipulate images. And a few years ago, I redesigned it, and we took a lot of inspiration from std.algorithm and std.range, which is to present everything as small composable components. Avoid implicit copying. So if you use a graphics library like GG, you will know it generally mutates state on every operation. And also, if you want to create a version of something, you have to create a copy. This does things in a functional manner. And the library starts out with the definition of a view. So a view is basically a concept kind of like a range, but it says that a view must have a width and a height, and we need to be able to access its pixels. And basically, that's all there is to a basic view. This is the basic composable component. In the same way, the definition is defined as a template, which verifies if a type implements this interface in the same way like isInput range implements verifying if a type implements the input range primitives. Then we can create properties which define templates which get properties of the view in the same way that there is std.range.elementType, which returns the element type of a range. This will take the element type of a view. So on that, we can follow up with defining writable views. Obviously, we need to be able to write we test if we can write to the pixel array, and direct views are those that define scan lines. So if you implement a scan line in your graphics primitive, you can also, of course, access pixels, and we can define a mixin which implements pixel access on top of basic scanline access. So if you add a type which defines scanlines, you can mix this in to get a complete view. And this allows us to have this allows us to define an image which actually stores things in memory, because you will want to store, most of the libraries, but we do want to store pixels in memory time to time. And we just implement the scanline primitive, and then we mix in direct view, and everything else just works. And we can also do things which generate image data out of thin air. So procedural is a template which takes a formula, and all it does is create a view which has a width and height and pixels, and when you create the pixels, it just calls that function. The simplest procedural view is one that returns a solid color. So if you want, so you'll have to do is specify the color, the width and height, and it returns a instance of procedural that all it does is take the coordinates, discard them, and return the color. because a solid view will have the same color in every point. We can also do things, create more composable components which take a coordinate pair and transform it. So for example, if you want to specify something like a crop or rotate or something like else, you do not operate on the colors, you only operate on the coordinates. Cropping a view is simply shrinking its weight and width and height and shifting the coordinates by some amount, which you can easily do with the warp mixin declared before. So all this does is implement the warp function here, as well as declare, well, the width and height, which calculate the coordinates. And one thing we do here is that we also, as an extra, say if the parent view is a direct view, we will also provide scanline access, because scanline access is basically a DRA in memory, and if some operations are much faster by using array operations. And if you crop an image that's already linear in memory, you should also get a view that's linear in memory, similar to how you would say that a view has a width, height, and stride in other graphics libraries. For simple transformations, we should not change the view size. We can simply define a helper function, which applies the user-specified formula to each pixel's coordinates. And the warp struct is declared here. So all we do is take the mixing expressions x-expr and y-expr from the template declaration, and we mix them in here and simply pass them on to the warp mixin. This allows I'm gonna skip this. And this allows us to define very simply defined functions which take the height, which do a horizontal flip. We simply say that we just change the x coordinate by subtracting width from it, and we do not change y. Vertical flip is the same. And of course, if you want to do 180-degree flip, you flip both coordinates. Now, the interesting thing about this approach is that because everything is done lazily, you do not do these operations immediately. This simply creates a view which returns the flipped image data. So if you flip an image twice, it's a no-op. It is optimized out. And if you define clockwise rotation, which takes something and flips the coordinates and just simply flips x and y and does a horizontal flip, that's one way to do 90-degree rotation. If you rotate a view 90 degrees 4 times, it will similarly be optimized out, though as far as I checked, only on LDC. So if you have a strong optimizing compiler, you will get very strong optimizations thanks to inlining and template programming. So who can guess what this will print to the screen? Using a templated imaging library allows us to do something silly like declare a color space of char. Any guesses? Okay, this is the result. Another example we can try to do here is, well, let's try to draw a little D logo. So we can declare the foreground and background color. I use 16-bit types, as I will show you. We declare an image to draw on. We eventually want to draw to some memory. And let's do a for loop. So let's make a little animation for over 32 frames. Thanks to std.concurrency, we can simply add that parallel to the end of for each to put it easily in multiple threads. So we can we draw this image, and then in the for loop we can rotate it depending on the number of frames, and then we downscale it and do gamma correct downscaling, because otherwise you will get downscaling artifacts. And we can put it to a file, so the result is an animation like this. But you can do more things. I mean, you can take, a video is basically a series of frames, and well, there's more ways you can work with video. You could interface with the FFmpeg MPI, but I was lazy and think this was actually simple, is to simply use wonderful std.process and say, hey, FFmpeg, could you please take this video and give it to me as a series of BMP images? So image to pipe does that, and we can easily read that. And this is the reader, this is the writer. And what we get is a range, a video which is represented as a range of frames. And you can use standard range manipulation algorithms on it, like map or things like that. So the while loop here could be replaced by simple copy, but I wrote it out because we want to add more things here. And well, I prepared a live demo, but unfortunately, it was not ready to be presented at 10 o'clock. It was scheduled for 11.
Perhaps you can show the live demo later during the lunch break to the live stream.
I will try to show the live demo on the on the lunch break. And we call YouTube DL to get the live stream, and we pass that on to FFmpeg, which gets us in a simple format. And well, we can get some, we can read some frames, which is, you know, the daemon mascot. We can read them in memory. And sure, let's add some IRC logs, and this was supposed to be the demo slide. And unfortunately, it doesn't work yet. So this concludes my presentation. I had some bonus slides, but there's no time. Thank you.
When you were reflecting the DLL, you were doing reflection on D modules, but where did you get those for DirectX?
From the D bindings library,
Okay.
Which was on D source.
Thanks.
We have another question. Yeah.
So when you, is this on? Yeah. So when you were like can you go back to part 3?
Sorry?
Can you go back to like the early part of part 3? Obviously the slides here.
I'm
so
sorry, I can't
when
hear
you.
you.
When you're doing the adder example, that was quite verbose. Is there any way to reduce the verbosity of that?
I'm sorry, I can't hear you. There's too much echo.
Sorry. When you were doing the adder example with the computation graph, is there any way to make that less verbose?
The computation graph. Oh, with the adders?
Yes.
Let's see, where was it? Oh, there was a beginning.
Part 3.
Part 3. Okay, I can hear you. Part 3. Yes, well, this is one of the, this is all experimental, so I've been looking for ways to make it less verbose. The way, I tried to use string mixins, but I tried to use template mixins, but I ran into problems with those. So separating these in data and implementation parts was the only way which I could allow these components to refer to each other and share the same this pointer. Let me find it. Yes, here. Yeah. Any other questions?
I think unfortunately we're out of time, Vladimir. So we'll take a short break, and then we'll come back for Scott's rescheduled keynote.